In this video, we will take a look at a distribution known as the exponential distribution, and it is not completely new to us. It's actually a special case of a distribution that we recently discussed, and that distribution is the gamma distribution. So let me remind you just what the PDF of the gamma distribution is. So if x is distributed as a gamma distribution with parameters alpha and beta, then its PDF is that fairly complicated function. So we have 1 over beta to the alpha times the gamma of alpha, and we have to know how to evaluate that gamma function. And then we have x to the alpha minus 1, and then times e to the negative x over beta. And this is whenever x is greater than or equal to 0, and then it is 0 otherwise, right? But if alpha is equal to 1, right, then this PDF, look at how it simplifies, right? In fact, let me do the simplification over here. So everywhere we see an alpha, we're going to plug 1 in. So beta to the alpha just becomes beta to the first power, which is beta. Gamma of alpha becomes gamma of 1, and we know that recursive property for the gamma function. When you have a positive integer there, the gamma of a positive integer is that positive integer minus 1 factorial. But that boils down to 0 factorial, which is 1. And then we have the x to the alpha minus 1, which is going to be x to the 1 minus 1, which is x to the 0, which is equal to 1. So a lot of the challenges, if you will, with the gamma distribution, they kind of go away when our alpha is equal to 1. And because technically, so this part goes away, the x goes away, and then all I have is 1 over beta, and then I'm left with this simple exponential function. So this is what it looks like, right? So over beta, and then this is, again, the sample space doesn't change. The only assumption that we're making is that we're saying that alpha is now equal to 1, and a lot of it reduces. And this is what the PDF looks like. And really, when you look at it, the only part of this PDF that has a functional term, right, is this exponential function. So it's not a coincidence that we refer to this special case of the gamma distribution as the exponential distribution, right? So if alpha is equal to 1, then the PDF reduces to this. And we say that x is an exponential random variable, or it follows an exponential distribution, right? And we write it this way. So x. So you could certainly use the gamma notation and put the 1 there and then put the beta, but since we never really use this, right? Many times what we might do, we might say that x is distributed, and we just use e for exponential, or the exp if you'd like, but the exponential, and then you just put your beta in the parentheses. So for all intents and purposes, the exponential distribution has one parameter, that's our beta, and this is how we can denote it. Now, let me remind you a couple other properties of the gamma distribution. The expected value of the gamma distribution is alpha times beta, and the variance of the gamma distribution is alpha times beta squared. So again, if I make the same substitution and replace alpha with beta, right, then we can get formulas for the expected value and the variance of my exponential distribution. Yeah, so here's its PDF. and its mean would just be 1 times beta, so that's just beta, and then its variance would be 1 times beta squared, so that would just be beta squared. And what else about this? Well, and the other assumption about the alpha and beta parameters is that they're both positive. So that holds down here as well, right? So again, just with this one simplification, we get a new distribution, a simplified version of the gamma distribution, and here are the formulas that follow by making this substitution. Now, the benefit of getting rid of this x factor of x here that's raised to the alpha minus 1 is that the integral of this function is now a lot easier, which means we can actually go through and compute its CDF. So, we can't write down the CDF for a normal distribution in a nice way, right? We can't write down the CDF of a gamma distribution in a nice way, again, simply because of how difficult the integral is. However, with this simplification, the function is a lot easier to integrate. And now let's see if we can find the formula for the CDF of our uh, exponential distribution, right? So since the sample space is only for, well, it's for values of x greater than or equal to 0, what we can say is this. When x is less than 0, the CDF will have a value of 0, right? Because again, there's no area under the graph of this. And the graph of this is fairly straightforward. It's an exponential function, and because of that negative sign there, it's an exponential function that is decaying, so it goes down, right? So let's find the CDF, which is the area function of our PDF. So the only other case we have to look at, thankfully, is just when x is greater than or equal to 0. So then the CDF will be the integral. I could go from negative infinity to 0, but from negative to infinity to 0, the function is 0. So the integral will be 0. So all I really need to go is from 0 up to my variable upper limit, and then I'll have to do my dummy variable switch and integrate the function 1 over beta e to the negative t over beta. That looks like an I, should be a t. T over beta, and then this is dt, right? So no integration by parts is needed. I can factor out the 1 over beta, that's just a constant. And then let's think about the antiderivative of the e to the negative t over beta. Formally, you can do a u substitution, but really, this function, right, can be written as e to the negative 1 over beta t. So that constant, when I integrate, right, essentially reversing the chain rule, I would divide by this constant. So when I divide by this constant, it becomes negative beta. Let me do that. And then I'll still have my e, so I'll have e to the negative, and again I'll write it like t over beta. So that's my antiderivative, and then we're going to evaluate this from 0 to x. Now look at what happens. I have 1 over beta here, and then I have a negative beta there. So when I multiply these constants, I'll get a negative 1. At the upper limit, I'll just have e to the negative x over beta, like that. And then minus, and then at the lower limit, now remember I already took out the negative beta, so e to the 0 is 1. And then if I distribute the negative sign, things just work out so nicely. I end up with 1 minus e to the negative x over beta. So such a simple function to use as it's a CDF, which makes computing probabilities so easy now because we actually have the area function computed in a nice closed elementary form. So let's write down our CDF as a piecewise function. So therefore, the CDF of my exponential function will be, or is, it's 0 whenever x is less than 0, and then it's 1 minus e to the negative x over beta whenever x is greater than or equal to 0. And this function, it can be verified. It has all the required properties of a CDF. All right, so let's take a look at an example. I mean, there's really not much more to say. Like, once you go through and you have your formulas for not just the mean and the variance, but if you're lucky enough to be able to compute the CDF of your continuous random variable, then you're good to go. But let's work through an example, just highlighting some of these main ideas. Right, so let's say a random variable is exponential with parameter, and let me write it as exp. I don't think we've used the letter e for any other random variable. Let's just say it's exponential, and let's say beta is equal to 4. So let's go through and first let's write down the PDF and maybe give a sketch and say a couple things about the properties of that function. So here is the PDF. It's 1 over 4 e to the negative x over 4, and this is for x greater than or equal to 0, and then it's 0 otherwise. Let's sketch this PDF and see what it looks like. So here is my xy plane, at least a portion of it. And there are my axes. So when x is less than 0, the PDF is 0. So again, it's along here, no area, no probability. And then notice when I evaluate this function at 0, I'll have 1/4. So that means it actually jumps up. So let's say it starts from here. And then, if you think about the graph of your basic exponential function, with the negative coefficient of x, it's an exponential decaying function. So it goes down like this. Right? And then, of course, it's asymptotic to the x-axis. Remember, simple exponential functions, not ones that are translated like up or down, they cannot cross or touch the horizontal axis. They're always positive, right? And that's your PDF. And so it's certainly not symmetrical. It does have a tail that stretches towards the right. So this sort of distribution is skewed to the right, much like the gamma functions that we previously discussed. I mean, if this is a special case of the gamma, special in the sense that it's simplified, right? But it still holds a lot of the general properties. So this one is skewed to the right. Right? So now let's write down what the area function is, which is the CDF. But I don't have to compute I don't have to redo the integral because we've done it in a general way, and we have the formula for the CDF right here. All we have to do is just substitute the specific parameter for this example. So the CDF is the function that is 0 whenever x is less than 0, and then it is 1 minus e to the negative x over 4 whenever x is greater than or equal to 0. And what does this function give me? Well, it gives me the area function, right? So again, I could do it on this, but again, this graph, I'm already using the letter x as my variable. So I'm going to switch it and show you again just another example of what this area function represents. Now, I'm not going to draw this function. I'm going to draw this exponential function but I'm going to call it f of t now. So essentially, think of this as the t-axis. And where's my x? My x is a number along that t-axis. So basically, that's my x. And my CDF gives me this area. Right? So it gives me that area from 0 to x. And again, maybe just for emphasis, I'll say that it's 0 there. Right? So whatever x I plug into this function and whatever number I get here, which we use as a probability, but it's also associated with this area, right? So the closer x is to 0, then the smaller the area, and then the larger x is, the further it's away from the origin, then obviously the larger the area. And the thing is, it's really not hard to prove. We could do a simple improper integral to show that the entire area under this function is equal to 1. So everything is valid, right? Let's now just compute a couple, some probabilities. So what is the probability that my random variable is less than or equal to 3? Okay. Well, again, let me set it up both ways to emphasize again the difference between the PDF and the CDF and how you use each of them to compute probabilities. And with the exponential distribution, you will always have a choice because you'll have the formulas for both of these functions. So you choose how you want to compute your probabilities. If you're using the PDF, then this probability corresponds to this integral from 0 to 3, because 0 is the smallest value, if you will, the smallest possible value of x. And then we would integrate the function 1/4 e to the negative x over 4 dx. But we just did this integral, so we will have the 1/4 here, but then we're going to have to, when we integrate, we're going to have to multiply by 4, right? The reciprocal of 1/4. So we're going to end up with negative e to the negative x over 4, and then that's evaluated at 0 and at 3. And at the upper limit, we'll have negative e to the negative 3/4. And then at the lower limit, we'll have a negative 1, but then we're subtracting that negative 1, so it becomes plus 1, right? So this ends up being 1 minus e to the negative 3/4. And as a decimal, let's see, this is 0.5276, right? So that's our probability. And that's what it would look like using the PDF. Using the CDF, what we would have to do is, since the CDF already accumulates the area for us, I just have to plug 3 into my CDF. So the probability that x is less than or equal to 3, that would be big F of 3. And it's not hard to see that we get the exact same expression. 1 minus e to the negative 3/4, right? And of course that's the same 0.5276, right? Let's say we wanted to find the probability that x is greater than or equal to 8. Well, lots of ways we could do this. If we're up for an improper integral, and who isn't always up for an improper integral, we go from 8 to infinity. And we would integrate again the same PDF, right? But then again, if you're not that up for an improper integral, but you want to do an integral anyway, and again, who doesn't always want to do an integral? Well, we can use the complement and say that the probability that x is greater than or equal to 8 is 1 minus the integral from, and then this would be from 0 to 8, right? The total probability is 1. So in other words, the area to the left of, to the right of 8 is equal to the total area minus the area to the left of 8. And again, this is a very useful property, the fact that when you can say that these sample spaces is like semi-finite. It's infinite, I should say, semi-infinite, because it's infinite in only one direction. So you can always avoid having to go to infinity by taking the complement, right? So you could do that. Or, so I'm not going to do that part, I'm just going to go ahead and say, well, another way we could do this is to use the CDF. And again, I would apply, now using the CDF, I have to use the 1 minus as well, because the CDF requires a less than inequality, not a greater than or equal to. So I would do this. And then this would be 1 minus big F of 8, which is 1 minus, and then the quantity 1 minus e to the, and then we plug our 8 in. So minus 8 over 4. But look at how this simplifies. The 1 goes away. That negative changes it to a positive e to the negative 2. And that's our probability, which is approximately 1.353. Right? Now, suppose we had to find percentiles of this distribution. Again, in general, percentiles can be tricky, and we've seen it. For instance, finding percentiles of like a normal distribution, where you have to rely on a table and you're hoping that you can find a value. Well, you can always find a number that's close, but you want it to be, you'd love it if it would be precise, but that's just the problem with using a table. And finding percentiles of a gamma distribution really difficult, because many times you end up having to use like a numerical solver to solve some difficult equation. But because we have such a relatively simple CDF, it makes finding percentiles of the exponential distribution, again, relatively easy. So let's find, let's say the 75th percentile. So to find the 75th percentile of the distribution of x, right? What do? Well, we would take our CDF, and so, our notation for the 75th percentile would be that x sub 0.75, and then that would have to be equal to 0.75. Yeah, so take the CDF, which is 1 minus e to the negative, and then I have and then in this case would be x 0.75 divided by the 4, and then that is equal to 0.75. So again, it's a little bit messy if you use the formal notation for your percentile, but if that doesn't bother you, go right ahead. Subtract 1 from both sides, so we have negative e to the negative x sub 0.75 over 4, and then this gives me negative 0.25. Multiplying both sides by negative 1 gives me e to the negative x sub 0.75 over 4 is now a positive 0.25. Taking the natural log of both sides gives me negative x sub 0.75 over 4 is the natural log of 0.25. And if you're worried about multiplying by this negative here, in fact multiplying by negative 4, don't worry, because the natural log of a number between 0 and 1 is always negative. So this is negative, and then when I multiply it by negative 4, then I'll get a positive value. Because we want to make sure that our percentiles have to lie within our sample space. And the sample space for the exponential distribution, just like the gamma distribution, is all non-negative real numbers. So our 75th percentile is equal to -4 times the natural log of 0.25. And then that is approximately 5.5452. And again, this is pretty remarkable. Let me go back and do another sketch. I'm in a sketchy mood today. So if we sketch the PDF, and it starts up here at 1/4, and then it decays exponentially like this. And remember, the entire sample space is 0 to infinity. And what we're saying is the number roughly 5.5, so roughly 5.5, that has 75% of the distribution to the left of it. Remember, that's what the percentile is, right? So the probability that my random variable is less than this number approximately is 0.75, right? So in terms of area, right? In terms of area, that green area is exactly 0.75. That means from 5.5 roughly to infinity, it would just be the remaining 0.25. Right? It's really remarkable that in this little finite region here, we have 3 times as much area as the infinite blue region there. Right? Just the wonders of these improper integrals and unbounded regions. Right? Well, that's our exponential function. Very, very straightforward. It's one of the easier continuous functions to work with because of how simplified the PDF is, everything becomes easily obtainable, and the integrals end up not being too difficult. The CDF being so simple makes it easy to compute probabilities and so forth. All right, and I'll see you in the next video.